Welcome. My name is Tristan Hornetz. I am a preparatory phase PhD student at the CISPA Helmholtz Center for Information Security, and I will be presenting Lixom, Protecting Encryption Keys with Execute-Only Memory, which is a paper that I co-authored with my colleague Lukas Gerlach and my PhD advisor Michael Schwarz. So as the title may already suggest, I will be talking a lot about execute-only memory in this presentation. So before we start, let's briefly clarify what that even is. So on most computers today, the memory access restrictions are configured in the write X or execute policy, which in simple terms means that for data, you can read and write, but not execute. And for code, you can read and execute, but not write. But if we take a closer look at that, we can see that the read permission for code is only utilized very rarely by actual software. And so what we can usually get away with is to just remove that read permission as well. And then we have execute-only memory, or XOM for short. Now, the idea of execute-only memory is already quite old, but seeing it used today in practice is rare. And that also means that execute-only memory has not been explored that much yet when it comes to defenses against all kinds of attacks. And here's where our paper comes in. We show that using execute-only memory on x86 specifically, you can create a very strong leakage protection scheme against privileged attackers even that protects cryptographic secrets. And furthermore, you can also use them to defend against microarchitectural attacks such as Spectre, Meltdown, and also others. All of that comes at a very low runtime overhead, so it's quite practical to use in practice as well. And in this presentation, I will be specifically, first of all, talking about some background on x86 and how execute-only memory is implemented there. I will then show you how you can use execute-only memory to protect cryptographic secrets. And then finally, I will show you some case studies that we built to hopefully convince you that this is quite practical to use in practice. All right, so how does execute-only memory work on x86? Well, in general, if you want to configure any sort of memory access protection on x86, you would configure that in the page tables. And for a number of years now, the page tables on x86 actually support execute-only memory through a feature called memory protection keys. But unfortunately, due to the way that these protection keys have been designed, it is possible for a regular user without any privileges whatsoever to make an execute-only memory page readable again. So while these protection keys are nice, it's challenging to use them for any security-related purpose, and so we don't use them. Instead, we rely on a feature called extended page tables. Now, the background here is that in virtual machines, your virtual address is translated twice. In the first step from virtual to so-called guest physical address, which to your guest looks like a regular physical address. But in the background, it is translated again to a real physical address, which is backed by memory and hardware. And the reason why that is interesting to us is because that second translation step uses the so-called extended page tables, which have a different format than the regular x86 page tables. And they actually allow you to configure execute-only memory in a way that is not plagued by security issues like with the protection keys. So the takeaway is that on x86, secure execute-only memory actually exists in virtual machines. And also, what's nice about this is that the protection is configured by the hypervisor, not the guest. Which means that if we configure execute-only memory, not even the guest kernel can read into it, which is a very strong property. Another really nice property of x86 when it comes to execute-only memory is that execute-only memory is completely immune against meltdown attacks. And the reason for that is quite simple. Meltdown can only leak from a specific microarchitectural buffer in your CPU. So to illustrate that, here is a schematic of the Skylake architecture, which is still widely used today and is also very affected by Meltdown. And the buffer from which Meltdown leaks its information is here. It's the L1 data cache. And if we compare that to the path that instructions take in the microarchitecture, we see that there's no intersection because the data cache is concerned with data and not with instructions. But with execute-only memory, the only way in which information can enter the core is in the form of instructions. So in other words, it is completely impossible to leak any information from execute-only memory using Meltdown. And the same goes for a lot of other sort of Meltdown-like attacks that may leak from other buffers in the microarchitecture. But since they all generally reside in the memory backend, which is concerned with data and not with code, you cannot use them to leak data from execute-only memory. So quite a strong property. So in summary, secure execute-only memory works, at least in virtual machines on x86. It's controlled by the hypervisor, not the guest kernel, and it's also completely immune against meltdown. And while all of that is nice, how do we actually use that to protect cryptographic secrets? Well, the idea is quite simple. We encode secrets into code, right? So instead of having a construct like this, where you have a key in data storage and an encryption function that would use that key, you would embed that key directly into the encryption function and protect it with execute-only memory. That way you can still use the key by calling the function, but you cannot read it again directly. So to specify that more clearly, our goal here is to allow the usage of a secret without disclosing it. And possibly we might want to even restrict the ways in which the secret is used. For example, we may want to have an AES key that can only be used to decrypt things. As the attacker, we assume an attacker with guest kernel privileges in a virtual machine, which attempts to leak that secret. And if you remember from before, that means that the attacker cannot read the secret directly, but it still has arbitrary code execution in our address space, and so is still quite a powerful attack model. However, we assume that the code in execute-only memory and also the hypervisor are trusted. And also, to clarify, we assume that the attacker already knows what code is in execute-only memory, just not that one secret that is encoded in this. So if we want to have AES, for example, our attacker would already know that. They would just not know the key that is embedded in our code. And unfortunately, because this is quite a strong attacker model, just putting the key into execute-only memory is not enough to protect it. So let's look at some things that might go wrong here. On the left, we have our untrusted attacker code, which calls into our protected execute-only code. And the execute-only code loads some secret into a register, uses it to encrypt stuff, and then returns again. And perhaps the most obvious thing that can go wrong here is once we return the secret, the encryption key in this case, may still be in the register, and then our attacker can simply read it, right? So before we return, we must make sure that our secrets are no longer in the register state. The same thing can also happen in memory. So if our code writes the secret to memory and we return again before clearing the secret, well, our attacker can read it, right? It's trivial. So we need to make sure that we clear it from memory as well. But unfortunately, putting things into memory is even worse than putting it into a register. Because what can also happen is that the attacker just creates a second thread, and while we are in the encryption function, reads that secret from memory. So putting secret things into memory that is not protected with execute-only memory is a bad idea in general. Here's another thing that can create trouble. It's a second function within our execute-only memory. And the problem here is that this function at some point returns again. And that return instruction will read a code pointer from regular memory. And well, what can happen here is that the attacker again spawns a different thread, and while the second function executes, corrupts the return address. And then the attacker can hijack control flow to a location that they control and leak the key similarly as you would do in the return to libc attack. So how do we defend against all of these attacks? Well, let's go about this a bit more systematically. So here's our example again. And of course, it has an entry point and an exit point from execute-only memory. But the area that we actually care about is the area where the key is in the register state. We call that the critical zone. And our goal is to ensure that no matter what happens, this key remains in the critical zone, cannot leave. And to ensure that, this critical zone has to follow some rules. And unfortunately, time does not permit me to tell you about all of them because it's quite a lot of rules that we have to follow here. But I will tell you about the two most important ones that affect the code in the critical zones the most. I've already talked about the first one, which is that we cannot write secrets to memory. And while that sounds like a big limitation at first, remember that x86 has vector registers. And so since they offer a generous amount of space, we can still store secrets like encryption keys or even intermediary results that might be secret in the vector registers. And the other rule that is very important is that exit points from the critical zone must purge secrets from the register state. That's very important. And while that rule may sound intuitive at first, it's actually quite hard to get right. Because if we phrase that differently, we must ensure that there's no branch instruction that can leave the critical zone under any circumstances, except by going through one of these exit points. And while that is quite easy to ensure for direct branches, where the destinations are sort of hard-coded, it is quite difficult to ensure for indirect branches where you have a code pointer. And so what we say as a rule is that you cannot have indirect branches whatsoever, which is, if you program these critical zones, quite a big limitation. However, despite it being so strict, it also has advantages. In particular, it also implicitly defends against spectre attacks, because if you only have direct branches and they all remain in the critical zone, you can ensure that the control flow stays within the critical zone, even speculatively. And so if you don't have a spectre gadget within your critical zone, you are completely safe from spectre attackers, which is also a very powerful property. So these are the two biggest rules. But unfortunately, even if we follow these rules to a T and everything is correct, there's still one final attack that our attacker can mount. So here's our code example from before again, and what the attacker can do, because they run in the kernel, well, they can just interrupt us while we're in the critical zone. And then, since our keys are always in the registers, we can just read them, which is of course bad. But to mitigate that, we can take into account the fact that this is not the full picture. The full picture actually looks like this. Because we are in a virtual machine, the interrupt first goes to the hypervisor, and then the hypervisor gives control flow back to the kernel. And so we can instruct the hypervisor for interrupts that come from a execute-only page to remove a part of the register state from the data that it gives back to the kernel. And that prevents our attacker from gaining access to that information. We call that register clearing, and in practice, we only do it for the vector registers and two general purpose registers. And while that ensures that our program does not simply crash, which would happen if we overrode the program counter, for example, it also destroys our entire progress, because if our intermediary results are the vector registers and we delete them, well, our progress is gone. And that's made even worse by the fact that we can't back up our state in memory, because that would disclose it to an attacker. So how do we solve this? Well, we can make one exception to that rule that we can't store stuff in memory, and that is if we previously encrypt this backup with a scheme like AES GCM that gives us confidentiality and integrity guarantees. So that ensures that the attacker cannot simply mess with our backup in memory, and we can still safely read it again later. And the nice thing about AES GCM in particular is that it has great hardware support on x86. So implementing that in practice is easier than it may sound at first glance. All right. And that is our approach. We use execute-only memory enforced by extended page tables. We have our programming rules and register clearing. And altogether, that gives us quite a robust defense that protects cryptographic secrets from privileged attackers and also from hardware vulnerabilities. And while that approach, as we have it now, only works in virtual machines, we can also create sort of a light version of our approach that also works outside of VMs. So here we use the protection keys to enforce our execute-only memory and also the programming rules, but we cannot do register clearing because we don't have the hypervisor anymore. And while that doesn't protect against privileged attackers, it still gives us the defensive properties that defend against hardware vulnerabilities. So for that particular purpose, we can also use this approach outside of VMs. All right. So let's look at some case studies that we built here. The first case study is quite simple. It's spectre protection for password hashes. And what we have here is just a password hash that is encoded into a sequence of instructions that gives us an equality check that we can then call with another password hash to check if our password is correct. So it's a simple equality test. It only has 21 instructions in execute-only memory, quite simple. And it still gives us all of the protection that we need against Spectre and Meltdown. And all of that at pretty much no runtime overhead, because it doesn't affect the rest of the program. And that makes it a lot faster than most of the other Spectre defenses. So quite simple, quite practical, and also quite fast. But note that this specific scenario is not really useful when defending against privileged attackers, because if you authenticate with your password and you type it in and your privileged attacker runs in kernel mode and can simply read that, well, it's not that useful. But against hardware attacks, it's quite strong defense. Our second case study actually defends against privileged attackers. It's AES encounter mode, and here we protect the encryption key. And also we implement this in a way that the encryption function can also be used for AES GCM, which means that we can use this also for authenticated encryption. And also, since we use register clearing here, we have to recover from register clearing events, and that is really easy because register clearing, the only thing that we have to do to recover is to reload the key, and then we can just continue at the last block that we encrypted because it's counter mode. So we don't lose that much progress when we get interrupted. That is not the case with our final case study, which is HMAC with SHA-256 as the hash function. And since we have a hash state here that is continuously updated, well, if we delete that, we have to start from scratch, which is of course bad. So we actually have to use our trick with the encrypted memory backups to make this practical. All right, so let's look at the performance of these things. Here's the throughput of our implementations. We tested that on 2 processors, but only the second one has the SHA-and-I instruction set extension, so only it can run the HMAC case study. And if we look at that HMAC case studies, we see that the throughput is a bit lower than with OpenSSL, but not by that much. So it's still quite practical to use. And if we look at the AES implementation, well, for CTR and also for GCM on the second processor, it's even a bit faster than OpenSSL, which was quite surprising to us when we first measured that. But then we looked into this a bit closer and realized that the bottleneck here is not actually the computation, but the latency of memory accesses when you load the ciphertext or the plaintext and then store back the encryption results. And apparently our implementation causes fewer cache misses than the OpenSSL one, at least on these specific processors. And so our implementation is a tiny bit faster than regular OpenSSL. So even though we have added security measures here, our code is not necessarily slower. It's even quite a bit faster. Unfortunately, we do still see some overheads when allocating new encryption contexts. And the reason for that is simple. Because our allocation lives in the hypervisor for Lixom, we have to do hypercalls to allocate new contexts, which is quite slow. And also for every key that we have, we need to make an entirely separate copy of our entire encryption code. And that, of course, is much slower than simply storing the key into memory, which we also see as overhead here. And unfortunately, that also translates to the real-world performance of our implementation. So here's Nginx, where we replaced the AES GCM implementation that is used for HTTPS with our Lixom implementation. And as you can see, we do see some overhead. It's still not that much, so this would still be practical to use in a real-world scenario. But we do have the overhead here. But note that this is kind of a worst-case scenario for our Lixom implementation, because what we measure here is the requests that Nginx can handle per second. And that means we have a lot of key exchanges here. And because the allocation of new encryption contexts is what is expensive here, this is kind of a worst case scenario. So although this is definitely an overhead, we can expect that for other applications where we don't have these frequent key exchanges, the overhead is quite a bit lower. So again, this is kind of a worst case scenario here. All right, and that is the end of my presentation. So to conclude, I've shown you Lixom, which is a protection scheme for cryptographic secrets that can even protect you from privileged attackers. It also defends against a lot of microarchitectural attacks. All of that at a very low runtime overhead. And finally, all of this works on existing hardware that you may have in your laptop right now. So it's also quite practical to deploy. And that is the end of my presentation. Thank you very much for listening. And if you have any questions, suggestions, comments, do not hesitate to contact me. I'm always open to feedback. All right. Thank you.